All right, students, let me try another one here. This has to do with power and efficiency, and it makes sense here. It's from chapter 7, number 51, and it says shoveling snow can be an extremely taxing because the arms have such a low efficiency for this activity. All right, so let me pause there because I think your author does a really good job of kind of trying to tie physics into the life science here, and he gives a bunch of physical activities. Even not just human activities, but all kinds of things like we have electric motors and diesel motors. But in the case of, say, cycling or climbing or swimming, and two options, above and below the water, shoveling, weightlifting, but it gives this number, this efficiency as a percentage. And so the one we're going to want to know is right here, shoveling. So shoveling is about a 3% efficiency. Keep that in mind. And what we mean by that is your energy is always conserved, and so you have a bunch of food energy. Well, we often call this a chemical energy because it's in the bonds of the food. And of course, thinking of conservation of energy, it got it from, and let's just say the food is corn, it would have got its energy from the solar energy. Of course, the solar energy gets it from the heat energy of the sun, and the heat energy of the sun gets that from the nuclear energy in the sun, and the path continues because of this principle of conservation of energy. So, starting with, say, nuclear energy in the sun becomes heat energy in the sun. The heat energy in the sun becomes solar energy. The solar energy then becomes a chemical energy in the food through the photosynthesis process. Then that food energy comes into us and through a whole chemical process, and something you guys probably have studied recently much better than I. You got the ADT, grabs another and becomes ATP, and there's that stored energy and blah, 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 blah. Anyways, and so all of that then eventually then makes the arms move and becomes kinetic energy. And there's our shoveling. However, in the process, there is a lot of heat energy and that whole metabolism process. So what they're saying here is in terms of efficiency is if we had, say, 100 joules of chemical energy that got metabolized in our body, 3%, so 3 joules would actually go into the shoveling process. And maybe I shouldn't say it's just kinetic energy, it's also a potential energy. So maybe you lift it up instead of giving it a sideways speed. Although I kind of picture here somebody shoveling and then they're going to throw it up and up onto a pile. So it starts as kinetic energy, which eventually becomes potential energy on this pile. But the point is it's 3%. And then your body gets the warmth, if you will. And in this case, if you're going to be shoveling snow, well, that warmth will definitely keep you warm out there. It may be too warm. If you were cold going out there, you might have on a heavy jacket, only to find out that that's, too much heat being trapped inside of your body, depending on the cold weather or not. Anyways, that's kind of this discussion about what do we mean by the efficiency. All right, so it says, and I'll start again. Shoveling snow can be extremely taxing because the arms have such a low efficiency in this activity. Suppose that a person shoveling a footpath metabolizes food at a rate of 800 watts. Now remember, a watt is a joule per second. All right, so we are using up food energy. We are metabolizing our food at 800 joules per second. A, what is her useful output power? Okay, so again, using this idea of 3% is actually useful and is moving the snow. The other 97% is just making heat. So if I take this 800 and multiply it by 3%, we're looking at 24 watts. Whoops, joules per second, watts. Going into actually moving the snow. the other, so 800 times 97%, that is 776 joules every second, is becoming heat in the body. Okay? So I guess I'll circle this for the answer of A. What is her useful power output? It's 3%. Okay. All right, so then B, and maybe I should put a little A here. B says, how long will it take her then to lift 3,000 kilograms of snow 1.2 meters? And so you're shoveling along in a path and you got to lift it up 1.2 meters and 3,000 kilograms of snow. Well, I'll use this as the idea that power is energy per time, or it's actually the work done per time. And in our case, we could look at either of these powers. I think the one to look at, though, is her power that is what they call useful output, because what we know is the corresponding useful work. We don't know anything about the amount of heat going on, but we do know that we've got to pile up this snow. So it's this energy, the 24 watts, that go into piling up the snow. So I'm going to put it as mgy. And so this is 3,000 kilograms times 9.8 and lifting it 1.2 meters. And just to check my units, here I would have a kilogram, here I'd have a meter per second squared, and another meter, and all that is equal to a joule. So if I rearrange this equation, excuse me, if I rearrange this equation, I can cancel a joule off, and I'm going to be left with units of 1 second when this 24 comes underneath and I flip and multiply. So let's go ahead, and when I say flip, I mean flip the units, not the number. The number is going to stay in the bottom. Okay, so here I'll take the energy 3,000 times 9.8 times 1.2 and say, all right, well, we need 35,280 joules of energy to pile this up. And I'm going to divide it by 24 because we're putting in, or this person shoveling is putting in 24 joules every second. So this is how many seconds it would take. It would take 1,470 seconds. And I suppose it might be fun to divide that by 60 and see how many minutes. All right, so we're going to clear this walkway in about 25 minutes. And so we're shoveling along for 25 minutes to get our snow and have a clear pathway. And I know for us who live in Santa Barbara, it's like we've never done this. We don't really know what this is, but this can be a big pain. Especially if there's ice even below and it's on the sidewalk. Ouch. And then you got to work extra hard. So you spend all this hour. You finally get a clear pathway so you or your loved ones don't slip on the pathway. And then, of course, half hour after that, it just snows again. And they're like, oh, bummer. And so that's why they have all these machines these days. All right. So there's the shoveling activity. On the other hand, you don't have to cut the grass in the wintertime. So you shovel snow instead of cutting grass. And so I find myself cutting grass the day before company comes on Christmas, and I guess other people find themselves shoveling snow the day before Christmas. All right, and then C, how much waste heat transferred in kilojoules will she generate? And again, I can kind of do the same equation. Power is energy times time, or work times time. But if I rearrange it, the work or the energy is powered multiplied by time. And so this time, instead of talking about the useful energy, we're talking about the waste energy. So I need to correspond. And I'll just say it again. Notice how my power of useful energy went with my work of useful work. And same thing here, my power of heat or waste energy is going to match my work energy. And that's what they want us to find right here. What is our waste heat? How much is that human body warming up? Which needs to transfer it to the environment. Otherwise, the body would overheat and the whole chemical process, the chemical reaction, doesn't work well. As I think you know, the difference between something hot and cold is the molecules bouncing around. And so our human bodies have a big problem if it is too hot or too cold. If it's too hot, the molecules bounce off each other and they hit so hard they break apart. And so instead of having these, complex, like the ATP and the DP and ATP, I think I guess the DP is the diphosphate or something like that, and triphosphate. But it's a complex molecule, and all of our proteins are. And so they bounce around like that, they'll break apart. And so if the body gets too warm, you can't sustain life. And I want to say something like 106 degrees Fahrenheit. If your core body temperature becomes that's sadly when you die. And so if you have a fever running at 104, that's a big concern, because you're getting dangerously close to that 106 Fahrenheit. Too hot is a problem. And of course, too cold is also a problem, because again, they have to hit hard enough to make the chemical reaction take place. So there's a fine line for the human body or any of the biochemical reactions as they come together. You want them to hit just at enough speed that they, not so fast they tear each other apart, but not so slow that they don't hit hard enough to actually do the chemical reaction. And so our body, as you know, has this great way of regulating its body heat. We can warm it when it's cold, and we can cool it when it's hot. And so in this case, it's going to get very hot, and we need to get that heat out of the body. And obviously, just taking off a jacket and letting the cold air is a start, but evaporation is the main key at how the human body cools itself. And so make sure you got plenty of fluids. And anyways, I digress in this. So let me go back to this problem. And so I'm looking at the waste heat. And so coming back up here to power, we are generating 76 joules every second of heat, of waste energy. And we're going to do that for 1,470 seconds. And so in terms of waste heat, 776 times 1,470 comes out to be 1.14 times 10 to the joules. And maybe as one more step, even though it's not asked, I might say, how many calories has this person done? So maybe this person's also trying to get some exercise, or maybe trying to lose some weight, burn some calories here. That would be kind of fun, because if I look at this, I could say the total amount of energy is this 800 joules every second. So there's both the waste heat and the useful energy, lifting the snow, in 1,470 seconds. And so the total, 800 times 1,470, would be this 1.176 times 10 to the, that should be a 6, right? 1, 2, 3, 4, 5, 6 joules. And to change this into what we would call nutritional calories, let me point out that I'll put joules in the bottom and little calorie on top. The little calorie, again, is a unit that scientists like, because it's actually how much does it warm up 1 gram of water. So we know 4.186 joules is equal to 1 calorie. So if I divide that by 4.186, I would get 280,936 calories. Wow. Now that means it would warm up this many grams 1 degree Celsius. And so going from a body temperature now of 37 degrees Celsius, well, your body would be a lot more than that many grams. Maybe I should say that would be 81 kilograms. If I take that to be roughly 4 times the human body, let's see if I lost myself here. But I guess I would say that if a body was this big, it would have warmed it up 1 degree. This is actually 4 times bigger than a human body, roughly, depending on the human. But actually, it's going to warm it up 4 degrees. So this would warm up your body to 41 degrees Celsius if you didn't lose some to the environment, which would put you over that threshold. Let's see, I guess, like I said, threshold, about 106 on Fahrenheit scale. And so, well, why don't we just kind of see what that is. On a Celsius scale of 41, let's see, Celsius, there would be 180 degrees Fahrenheit to boil water for every 100, and it would be offset by 32. Yeah, so, well, we're right there. We're at 106, so this would put us, well, anyways, obviously we got to lose body heat. Going to run into troubles. Anyways, that wasn't quite the direction I was going with this. That was kind of curious. But what I was doing was trying to just kind of point out these units of calories again. Again, small calories becomes very useful from a science perspective because we say how much a gram of water is. And I was treating the human body there as mostly water. Actually, I was treating it as purely water since it is mostly water. But now, from a nutritional point of view, let me put a little calorie and a capital calorie because there is 1,000 little calories here. And so let me go back up to this number here. And now divide it by 1,000. Oh, I guess I could do that in my head. And that is the 281 capital calories. So after shoveling all this snow for nearly a half hour, we have burnt about the equivalent of half a piece of chocolate pie. So if we're trying to lose weight, we could run into troubles if we go out there and shovel and say, I did a lot of work, I deserve a piece of chocolate cake, because you're going to get way more calories in that piece of chocolate cake than you just burned after shoveling for a half hour. So got to watch your food intake. That's more important than your exercise. There's just a lot of energy in food. All right, well, I babbled on too long. Hopefully all those were helpful, and good luck.